Hi there, Jim Caffey here. We're going to talk about Chapter 3 today on the science of astronomy. So, the goals for learning on this chapter are: in what ways do all humans use scientific thinking, and how is modern science rooted in ancient astronomy? So, we're going to look at scientific thinking based on everyday ideas and observation and trial and error experiments. How is modern science rooted in the ancient astronomy? Well, astronomy happens to be the oldest of all the sciences. It was often practiced for practical reasons, in keeping track of time and seasons, and other practical purposes like including agriculture, knowing when to plant your seeds, and then also for religious and ceremonial purposes. Also helped the navigators in the ocean to navigate according to the star spots. So ancient people of Central Africa, 6500 BC, would predict seasons from the orientation of the crescent moon. Pretty cool little idea there. They knew when the rainy season was coming and when the dry season would come. And the days of the week were named for the sun, the moon, and the visible planets, which were at that time Mars, Mercury, Jupiter, Saturn, and Venus. And you can see here how the days of the week came to be. Sun was Sunday, moon was Monday, and so on and so on. You see that there. So what did the ancient civilizations achieve in astronomy? Well, they could do daily time tracking. They could track the seasons in the calendar, monitor the lunar cycles, monitoring the planets and the stars, and predicting eclipses, and much more. So here is a very, very, very old Egyptian obelisk. The shadows, therefore, tell the time of the day. And you can see the different posts around the obelisk telling us the time of day. Pretty cool. Stonehenge, we've all heard about, completed around 1515 BC. And we do believe it is some kind of ancient calendar where the solstices and the equinoxes line up. In Mexico, they have the model of the Templar Mayor, and this is also an ancient way of telling time and seasons. In New Mexico, we found this device that aligned north and south. In the southwest United States, the sun dagger marked the summer solstice. In Scotland, 4,000 years ago, stone circles moonrises are shown here every 18.6 days, so it was a calendar. In Peru, lines are patterns and some aligned with stars, that was a calendar. Machu Picchu in Peru, structures aligned with the solstices. You know, again, for these guys 6,000 years ago, that was pretty high tech, I think. That's pretty good. In the South Pacific, Polynesians were very skilled in the art of celestial navigation. In France, cave paintings from 18,000 BC may suggest knowledge of our lunar phases, 29 dots. In China, the earliest known records of supernova were recorded in the explosions in rocks, 1400 BC, and we see that a new star would appear in the drawings in the rock. So what have we learned in this chapter? In what ways do all humans employ scientific thinking? Scientific thinking involves the same type of trial and error thinking, but that we use in our regular day lives, but in a carefully organized way. And how is modern science rooted in ancient astronomy, the oldest of the sciences, as it has important practical applications for developing civilizations? So now let's take a look at the ancient Greek science. Why does modern science trace its roots to the Greeks, and how did the Greeks explain planetary motion? We'll get into that. So our mathematical and scientific heritage originated with the civilizations of the Middle East here. Mesopotamia, Babylonia, Persia, Jerusalem, the Nile Delta, and Alexandria. This is an artist's reconstruction of the Library of Alexandria, the most important library in the world at the time. So, the Greeks were the first people to be known to make models of the universe. They try to explain with these models, which are simplified forms of the real thing, they try to explain patterns in nature without resorting to myth or the supernatural. And so the Greek geocentric model started about 400 BC with Ptolemy. Now, here's a special topic. One of the Greeks was named Aristosthenes, and he tried to measure the Earth's circumference in 240 BC. So he made measurements in the cities of Sion and Alexandria, a distance of 5,000 strata, which they used at the time, but the angle was about 7 degrees. So if you do all the math and you calculate the circumference of the Earth, you can get a decent number. Now, compared to the modern value, it's pretty far off. 250,000 for the Greeks, 42,000 kilometers for the modern value. But still, it was a pretty accurate and neat observation that Aristosthenes made. So how did the Greeks explain planetary motion? The underpinnings as such of the Greek geocentric model, under Plato and Aristotle, says that the Earth was the center of the universe, and the heavens must be perfect. Objects move on perfect spheres or in perfect circles. And at the time, this is when the church controlled the world. They controlled all the astronomy and the science. And so, of course, Earth had to be the most important thing in the universe. We were at the center. And the heavens must be perfect. They call these orbits God circles. And since God made them all, that they had to be perfect, right? Right. But this made it difficult to explain the apparent retrograde or backwards motion of the planets. So, over a period of 10 weeks, Mars appears to stop, back up, and then go forward again. And this cannot be explained in the Ptolemaic models. So the most sophisticated geocentric model was made out of Ptolemy, I just mentioned. Ptolemy lived 100 to 170 AD, the Ptolemaic model. It did sufficiently accurately model the remaining use for 1,500 years. So get this straight. Ptolemy, this philosopher, his theory of the universe lasted for 1,500 years. Nowadays, it's not even possible for us to get a prediction right for 10 years. But the Arabic translation of Ptolemy's work named the Almagest the greatest confirmation of his work. So, but why do the Ptolemaic models explain retrograde motion? Planets really do go backwards in this model. So what he had here were these orbits and these spheres. The planet would go in these little orbits around this bigger sphere and then come back and retrograde motion there in the loop and go back and forth and retrograde motion in the loop. Wasn't quite accurate. So the Muslim world preserved and enhanced the knowledge they received from the Greeks while Europe was in the Dark Ages. And the House of Wisdom in Baghdad was a great center of learning around AD 800 years ago. While with the fall of Constantinople in Istanbul in 1453, the Eastern scholars headed west to Europe, carrying knowledge that helped reunite the European Renaissance. So what have we learned in this part? Why do the modern science trace its roots to the Greeks? Well, they developed models of nature that emphasized that the predictions of models should agree with observations. And that's true wherever you go. The model observations should agree with the predicted observations. And the Greeks explained this planetary motion and the retrograde motion as the Ptolemaic model had each planet move around in a small circle whose center moved around Earth on a larger circle. And that held for 1,500 years. Until, Copernicus came along. The Copernican revolution came along, and our goals for this part, for Copernicus, how did these guys figure it out? Copernicus, Tycho Brahe, Johannes Kepler, how they changed the Earth-centered model. What are Kepler's 3 laws of planetary motion? I'm going to stress to you now, this is the most important 3 laws you're going to learn all year. And yes, one of them is a equation, but we'll get through it. And how did Galileo solidify the Copernican revolution? How did he really instill this is really what it is? We'll figure that out. So, how did we change this Earth-centered model? Copernicus lived from 1473 to 1543, and Copernicus proposed a sun-centered model, published in 1543. Man, this had the church up in arms. They didn't know what to do with this guy. He used the model to determine the layout of the solar system, planetary distances, and AUs, but the model was no more accurate than the Ptolemaic model in predicting planetary positions because it still used perfect circles, those God circles. So could there be something different? Do they have to be in perfect circles? Well, if God made it, then yes, but is that scientifically accurate? And the answer is no. Tycho Brahe came along. Tycho Brahe was an observational astronomer. He was the Greek astronomer for the King of Denmark. So Brahe compiled the most accurate, very detailed naked eye measurements ever made of planetary positions. He had 40, 50 years of data in this. He still could not detect stellar parallax, from stars moving back and forth. And so he thought the Earth must be at the center of the solar system still, just like Copernicus did. But he recognized that the other planets did go around the sun. Tycho, the observational astronomer, hired Johannes Kepler. Okay, well here is the tricky part. Kepler used all of Tycho's 50 years of observations to discover the truth about planetary motion. And he developed 3 laws to discuss this. Okay, but what's the problem here? Why did Kepler steal all of Tycho's stuff? Well, as I told you, as the rumor has it, Tycho Brahe was the Danish king to the King of Denmark. Danish astronomer to the King of Denmark, excuse me. And the king liked to enjoy big feasts with lots of meat, and lots of ale, and he would drink and eat all night long. He was a big guy. And Tycho was invited to this dinner, and the rule was that you did not get up from the dinner table until the king left. And this is a story you're only going to hear here at summer semester OTC. So here's what happened. Tycho went along with the king, drank his ale, had his turkey legs, and at some point in time, Tycho had to go relieve himself in the bathroom. The king had not gotten up. He could not go do such a thing. After a while, he got in a lot of pain. You know how this is going to end. And bam! His bladder exploded. Tycho died 3 days later of an infection. So Kepler, basically a glorified graduate student, said, I'll take his data. I'll take all of it. And he did. So here's Johannes Kepler, 1571 to 1630. Kepler first tried to match Tycho's observations with a circular orbit, the way everybody said it was. But there was this error in the measurements he could not get it to do. So Tycho said, and I quote, if I had believed that we could ignore these 8 minutes of arc error, just some error, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore those 8 minutes, point out the road to complete reformation in astronomy. And so we come up with Kepler's 3 laws of planetary motion. I'll make this real simple for you. Law 1 says the orbits of the planets are ellipses, not circles, with the planet at one focus point. So in an ellipse, there are these focus points that anchor the ellipse together, and the planet sits in one of them. In the other focus, there's nothing there. So Kepler's first law of motion said the orbits of the planets are an ellipse and not in a circle. So here's what that says. Kepler's second law basically says it's an equal area and equal time law, which says this. If the planet sweeps out this much space in 3 months, This area, the gray part, must match all this gray part 6 months later when it sweeps out a 3-month orbit. What it really means is that the planet has to go faster around near the sun and slower away from the sun. So imagine this is a chunk of pizza. You like pepperoni pizza? I do. This chunk of pizza is the exact same amount of pizza as this chunk. Next time you have some pizza with your family or your friends, I want you to carve out a piece of pizza just like this and say, well, they're equal size, and see if they argue with you, because I guarantee you they're going to, especially the kids. They're not going to understand it. But you'll be there to teach them. Kepler's third law, here comes the equation. There are thousands of equations in all of astronomy. I'm going to ask you to remember one of them and know how it works. The most distant planets orbit the sun at a slower average speed, obeying this relationship. P squared equals A cubed. P is the orbital period in years. A has sometimes been called the semi-major axis. If you're really good at geometry, you know what that means. We'll break it down in simpler terms as the average distance from the sun in astronomical units. So for the Earth, we orbit the sun in 1 year. 1 squared is 1. Our average distance from the sun in AU, by definition, is 1. So 1 squared equals 1 cubed, all equals 1, and it works. Where this gets a little tricky is when we get out past Saturn, Uranus, Neptune, and Pluto. And really, for Pluto, it completely fails. Neptune, too. So how did Galileo solidify the Copernican revolution? Galileo came on next. Galileo, now here's a misconception. Galileo did not invent the telescope. He was the first scientist to use the telescope, but it was actually Italian lens makers who did make the first telescope. But Galileo, 1564 to 1642, overcame major objections to the Copernican view. 3 key objections were rooted in the Aristotle view of the universe. Number 1, Earth could not be moving because objects in air would be left behind. 2, non-circular orbits are not perfect as heaven should be by the God circles made by the Lord, as the church stated. And 3, if Earth was really orbiting the sun, we would detect stellar parallax, and that's that shift in starlight. So, overcoming the first objection, Galileo's experiments showed that objects in the air would stay with a moving Earth, and that Aristotle thought that all objects naturally come to rest. But Galileo showed that objects will stay in motion unless a force acts upon to slow it down. This actually is Newton's first law of motion. So Newton has his own 3 laws of motion. One of them is an equation, you guessed it. So basically Galileo says objects in motion will stay in motion, objects at rest will stay at rest until acted along by an outside force. The second objection of heavenly perfection. Tycho's observations of the comets and supernovas already challenged this idea. So Galileo got his telescope out and he said sunspots on the sun are imperfections, not perfect. And there are mountains and valleys on the moon, proving that it is not a perfect sphere. Boy, we're going to start taking some people off about right now, especially the church. Overcoming the third objection of parallax. Tycho thought he had measured stellar parallax distances, but the lack of parallax seemed to rule out an orbiting Earth. But Galileo came along, showed that stars must be farther away than Tycho thought, in part by using his telescope to see that the Milky Way galaxy is countlessly individual stars. And so if stars were much farther away, so they were really back away from here, then the lack of detectable parallax would be no longer so troubling. They would have such a small parallax to not be able to detect them. Galileo also saw 4 moons, the Galilean moons, Europa, Ganymede, Io, and Callisto, proving that all not objects orbit the Earth. And Galileo's observations of the phases of Venus showed that the orbits of the Sun Venus orbits the sun and not the Earth, because he did see phases of Venus. Well, Galileo got in some trouble. In 1633, the Catholic Church ordered Galileo to recant his claim that the Earth orbited the sun. His book on the subject, though, went wildfire. It was removed from the Church's index of banned books in 1824. Galileo was formally vindicated by the Church in 1992 at the hands of Pope John Paul II. And now these days you can go to Rome, you can go to Vatican City. They have their own telescope in Vatican City with their own astronomer who works for the Roman Catholic Church. And they have also now shown for a couple of years an exhibit showing Galileo's work. Now, technically, while they say that he was vindicated by the Church in 1992, what really happened was in 1979, Pope John Paul ordered an investigation. It took 13 years to come to a conclusion. The Church never ever said, well, we were wrong, Galileo was right. What they did say, though, was he probably was right. And that's kind of it. So still here in the year mid-2015, we don't have a formal thing from the Church saying we were wrong, he was right, we screwed up. Doesn't happen. So what did we learn? We learned that Copernicus created a sun-centered model. Tycho Brahe provided the data needed to improve this model, and Kepler, who was hired by Tycho, Kepler was a mathematician, he found a model that fit Tycho's data. The three laws of planetary motion, very important to get these. The Kepler's three laws of planetary motion. You will be asked this on every single quiz, every single test, every single exam, and the midterm and the final. So it's time to learn it. 1. Orbit of each planet is an ellipse, not a circle, with the sun at one focus. 2. As a planet moves around its orbit, it sweeps out equal areas in equal times. That chunk of pizza you're supposed to get with your kids. And 3. More distant planets orbit the sun at a slower average speed. That p squared equals a cubed, and you will see this in your Mastering Astronomy homework. Do not be freaked out by this. This is something very simple you can do on your calculator or your phone. And if you run into problems, I'm here to help you. It's what I do. And so that's really the one big equation for you. Galileo solidified the Copernican revolution by his experiments with the telescope and observations that overcame the remaining objections to the sun-centered solar system. The nature of science, we're going to look at how can we distinguish science from non-science, or nonsense, and what is a scientific theory. So defining science can be surprisingly difficult, really. Science comes from the Latin scientitia, meaning knowledge, but not all knowledge comes from science, as you may know. So we have this thing called the model, the idealized scientific method model, based on proposing and testing hypotheses. Because a hypothesis is an educated guess. You probably heard that in school a long time ago. And so the process goes like this. You make an observation, you ask a question about it, you suggest a reason for what you're seeing, and you make a prediction. If the prediction fails, you go back to the hypothesis and make a new educated guess. Otherwise, you can make additional predictions and test them if it works. But science rarely proceeds in this idealized way. For example, sometimes we start just looking around and then coming up with possible explanations. Sometimes we follow our intuition rather than a particular line of evidence. So, modern science seeks explanations for observed phenomena that rely solely on natural causes. A scientific model cannot include divine intervention. Period. Faith and science are two different things. Hallmark number 2. Science progresses through the creation and testing of models of nature that explain the observations as simple as possible. And this is called Occam's razor, meaning the most simplest prediction is probably the one most correct. You may have heard this term in the movie Contact with Jodie Foster. Number 3, a scientific model must make testable predictions about natural phenomena that would force us to revise or abandon the model if the predictions do not agree with observations. Very important. So finally, to wrap up, we've learned that science seeks explanations that rely solely on natural causes, progresses through the creation and testing of models of nature, and the models must make testable predictions. A scientific theory is a model that explains a wide variety of observations in terms of a few general predictions and principles, and that has survived repeated and varied testing.